Welcome to Spaceverse, your portal to cosmic adventures. Remember back in 2019 when we got our first ever image of a black hole? It was the supermassive black hole at the heart of the galaxy Messier 87, made possible by the Event Horizon Telescope. Then in 2022, we got another image, this time of the black hole at the center of our own galaxy, the Milky Way, called Sagittarius A. The two images looked a bit different, mainly because Sagittarius A is less massive and smaller in size, so its appearance changes more rapidly over time. Over the past 5 years, the EHT team has published numerous detailed papers explaining how they collected their data, the gaps in that data, and how they use machine learning to fill those in. They've also given many talks, both academic and public, to share how these groundbreaking images were produced. But just recently, a group of Japanese researchers, Miyoshi Kato and Makino, published a paper claiming that they couldn't recreate the Milky Way black hole's ring-like image using the same public EHT data. Instead of the iconic glowing orange ring, their results showed something more like a blob. Interestingly, this isn't the first time they've raised concerns. Back in 2022, they made a similar claim about the EHT's image of the black hole in Messier 87. In short, this Japanese research team is basically arguing that the iconic black hole images released by the Event Horizon Telescope, the ones of Messier 87 and our own Milky Way, are incorrect. The Event Horizon Telescope collaboration has responded to these claims, both back in 2022 and again just recently in 2024. They say the Japanese team misunderstood how the EHT data works and how it should be analyzed, and that their criticisms are not valid. So, there's a lot to unpack here. In this video, we're going to go through everything step by step. First, we'll quickly review what you're actually seeing in those famous black hole images. Then, we'll talk about how the EHT functions and how those images are generated. After that, we'll look at what exactly Miyoshi, Kato, and Makino are saying is wrong with the images. And finally, we'll go over how the EHT team responded and what this all means going forward. I wanted to make this video because a lot of you reached out when this story started making headlines. And with so many conspiracy theories floating around online claiming these black hole images are fake, how can you tell whether this new criticism is grounded in real science or just more noise? Alright, let's jump in by first recapping what exactly you're seeing in those famous black hole images. You might be asking, how is it even possible to take a picture of a black hole? After all, a black hole is an incredibly compact object with such intense gravity that nothing, not even light, can escape it. According to Einstein's theory of special relativity, nothing can travel faster than the speed of light, which means anything that crosses into a black hole is essentially lost to us forever, including light itself. That's why we can't actually see the black hole directly. But what we can see is the glowing material swirling around it. As matter spirals in toward the black hole, the immense gravity causes it to speed up, almost to the speed of light, creating a lot of friction. That friction heats the material so much that it emits light, specifically radio waves, which is what the Event Horizon Telescope detects. That bright orange ring in the image, that's the glowing hot gas surrounding the black hole. And the dark patch in the middle? That's what we call the shadow of the black hole. It marks the boundary of the event horizon, the point of no return. It's not an actual surface, but rather a spherical boundary around the black hole where light and all information disappears from view. This shadow in the center of the black hole image represents the boundary where, to escape, something would need to move faster than the speed of light, which, according to physics, is impossible. So what we're really seeing in these images is a glowing ring of radio light surrounding a dark center. The bright ring comes from superheated gas swirling around the black hole, and the dark spot is the black hole's shadow. There are two famous images like this. One is of the supermassive black hole in the galaxy Messier 87, which is about 6.5 billion times the mass of our Sun. This was the first image ever released back in 2019. The other is Sagittarius A, the black hole at the center of our own Milky Way galaxy, which has a mass around 4 million times that of the Sun. That image came out in 2022. Now keep in mind that these are radio images, not visible light. So the colors you see in the pictures don't reflect what the black holes actually look like. The color scheme is artificial, just to help us understand where the radio signal is stronger or weaker. Typically, the images go from black, where there's no light, to orange, where there's some light, to white, where the signal is strongest. This makes the differences easier for our eyes to pick up. Now that you have a good idea of what you're looking at, let's get into how the Event Horizon Telescope actually makes these images. And to do that, you need a telescope that's really big. The EHT solves that by linking together radio telescopes all across the globe, creating one giant Earth-sized telescope through a technique called interferometry. The larger the telescope, the finer the details it can capture in the sky, essentially, the higher the resolution. It allows you to observe much smaller structures more clearly. Even though the Milky Way's supermassive black hole is about 4 million times the mass of the Sun, its event horizon, the dark central region we're trying to image, has a diameter of only around 160 million kilometers, roughly the size of Mercury's orbit. And because the center of the Milky Way lies about 27,000 light-years away, this makes the event horizon appear extremely small from our perspective. To resolve such a tiny feature at such a vast distance, an enormous telescope is required. In fact, in terms of how much of the sky this black hole spans, it's far less than a single degree out of the full 360-degree view of the sky. Building a telescope the size of the Earth isn't possible, so instead, astronomers use a technique called interferometry, which links together multiple radio telescopes spread across the globe. This method simulates one giant Earth-sized telescope. You can imagine the Earth like a giant disco ball, with each mirror segment representing a telescope pointed at the same object in the sky. Of course, we don't have telescopes covering every single part of the Earth's surface, so there are gaps in the data. However, as the Earth rotates, those gaps are partially filled in over time, allowing astronomers to gather more complete information. As you can see, not all of the gaps in the data are filled, which means there are still missing pieces in the image being created. To address this, the Event Horizon Telescope team developed a machine learning algorithm, an AI model that was trained on a vast range of images, from everyday Earth-based photos to astronomical images, and even simulated black hole models. This algorithm helps estimate what the missing data might look like based on the existing information already gathered. Katie Bouman, a computer scientist on the Event Horizon Telescope team, has given a great TED Talk explaining how this algorithm works. If you're interested in learning more, I'll link to it in the video description below. Now that you understand what the images are and how they were created, let's dive into Part 3, what the new study by Miyoshi, Kato, and Makino claims is wrong with the black hole images. This new study reanalyzed the raw data from the Event Horizon Telescope, which has been made publicly available, and tried to recreate the image released by the Event Horizon Telescope team in 2022. The same research team had done this for the Messier 87 data in 2022 as well. In both cases, their conclusions were the same. They couldn't recreate an image that resembled the ones released by the Event Horizon Telescope team in 2019 or 2022. They couldn't recreate the donut-shaped or ring-like structure. Instead, they ended up with something that looked more like a blob. The Event Horizon shadow wasn't resolved. And remember, this is radio light, not visible light, so the colors used don't have any intrinsic meaning. They're just a way to represent the data. If desired, the same data could be colored with the same black, orange, and white scheme as the Event Horizon Telescope images for a more direct comparison. Since they found this blob-like shape in their image, Miyoshi and his team claim that the Event Horizon Telescope might not be large enough or have enough resolution to clearly resolve the Event Horizon shadow. They suggest that the ring-like structure found by the Event Horizon team in both Messier 87 and the Milky Way's black hole is merely an artifact, not actually present in the raw data. They argue that the size of the ring detected by the Event Horizon Telescope matches the size of something called the point spread function, which refers to how much a telescope blurs an image. When you observe something with a telescope, light passes through lenses or reflects off mirrors, which can distort the image. This causes individual points of light to spread out and become more blob-like. In the case of visible light telescopes, this results in a slightly smeared center surrounded by faint, outlying patterns known as an airy disk. The astronomers were very familiar with this process. It's part of their expertise. This understanding is why we were able to predict the shape of stars in JWST images before the telescope even launched. The JWST's hexagonal mirror arrangement and supporting struts affect how light enters the telescope, which we knew would impact the image. With a radio interferometer telescope, where multiple telescopes are combined and we imagine the Earth as a giant disco ball, the situation is more complex. The distances between the telescopes vary and they differ in size. Additionally, there are gaps in the array, which makes the point spread function much more complicated. In radio interferometry, the PSF you get after applying a Fourier transform to the UV coverage has more intricate features. This means that any raw image you get from combining all the radio dishes will have the shape of the observed object merged with the distorted shape caused by the PSF, the way the telescope responds to incoming light. These initial dirty images in radio interferometry contain artifacts from the PSF, which aren't real features of the object. To clean these images, the artifacts are removed through a process known as deconvolving the PSF, helping to recover the true shape of the object we're observing. In their paper, Miyossi, Kato, and Makino show the point spread function and a dirty map. To create the dirty map on the right, they assume that the object being observed is a single point source of light. The result shows a bright red blob at the center, surrounded by areas of less light, and then brighter sections further out. They argue that the distance between the outer red areas in this PSF matches the size of the ring seen in the Event Horizon Telescope's original images. This, they claim, implies that if the machine learning algorithm is trained on images with ring-like structures, it might fill in gaps and generate a ring-like shape, even if it's not present in the raw data. Miyossi and colleagues suggest that even if the observed shape is blob-like the PSF, combined with a machine learning algorithm trained on ring structures, could artificially create a final image with a dot or ring-like structure. So, what was the Event Horizon Telescope team's response to these claims? Well, in June 2022, just 6 weeks after the first Miyossi paper about Messier 87 was published, the Event Horizon Telescope team posted a blog on their website. They emphasize that they encourage anyone to access their raw data and perform independent analyses to confirm their findings. This is an essential part of scientific research, reproducibility, ensuring that others can replicate the results and validate their conclusions. The Event Horizon Telescope team hasn't just made their data public. They've also released all the analysis code and the machine learning algorithm they used. In their response to the study published by Miyossi and colleagues in 2022, the EHT team stated that their reanalysis was based on a misunderstanding of the EHT data and methods, leading to incorrect conclusions. Essentially, they rejected the claims from Miyossi, Kato, and Makino, but they didn't provide much detail on why they disagreed. This led to another rebuttal from Miyossi, Kato, and Makino 6 weeks later, in which they challenged the EHT team's claim that their understanding of the data and methods was flawed. They also asked the HT team to clarify their response and provide more detailed reasoning. After that, things went quiet for a while. However, in a 2024 paper, the EHT team briefly mentioned the external analysis by Miyossi and colleagues, noting that it didn't support the EHT interpretation. The next major development came earlier this month when Miyossi, Kato, and Makino published a new paper analyzing the Sagittarius A data. In response, the EHT team posted another blog on October 29, 2024, offering much more detail than before. At this point, and this is just speculation on my part, I think the EHT team had been preparing this detailed blog post because they are working on a full research paper to address all of Miyossi and collaborators' claims. The research paper will likely take quite a while to complete because the team needs to be extremely careful with their analysis and confident in their claims. There will be a lot of thorough work involved. Additionally, any written material will need approval from all the senior members of the collaboration, which will add even more time to the process. This is just my assumption, but I believe this is why the EHT team provided more detail in their recent blog post. They start by listing the issues they have with Miyossi's latest paper, such as overlooking the variability of the Milky Way's black hole and not using the complete set of imaging data, only the data from one night. They also address inaccuracies in how Miyossi and collaborators describe the Event Horizon Telescope team's analysis methods. While they later dive into more details on each point, the main issue to focus on is the point spread function. They clarify that they do correct for the PSF shape in their analysis, just at a different stage than Miosi and collaborators do. Additionally, the EHT team examined the polarization of light around these black holes, which contributed to the distinct quant image rather than a donut shape. When they applied the same algorithms used for the black hole images to the polarization data, they obtained a blob-like image instead of a ring-like one. This led them to conclude that the algorithms are not mistakenly creating rings that aren't present due to the PSF. The Event Horizon Telescope team argues that this ring-like structure appears regardless of the assumptions made about the shape of the object being observed. I'll post links to all the papers and blog posts below so you can read them yourself, as one of the reasons I made this video is to share this ongoing discussion between the two research teams. I know many of you will be asking, but what do you think? Who's right? The thing is, while black holes are my research field, radio astronomy is not. I'm a visible light astronomer working with telescopes that observe invisible light and sometimes infrared or UV. I deal with things like spectra, data cubes, and standard images. I'm not an expert in interferometry, the process of combining different telescopes from around the world into a single, giant telescope with all the complexities that come with it. So I can only take what both research teams have said at face value, assuming they believe they've done the right thing, but I don't have the experience to know what the correct approach should be. If I had to make a decision, though, my instinct is that the Event Horizon Telescope team, made up of over 300 experts in radio interferometry and computer science, has spent years figuring out not just how to do this, but the best way to do it. They've been thinking about it before, during, and after collecting their data. And I believe the Event Horizon Telescope team is most familiar with their own data, so I'm inclined to slightly favor their side of the argument. However, this is why science depends on having many experts in radio interferometry from different collaborations and institutions around the world. These experts can evaluate both sides of the debate, offer their perspectives, and work towards reaching a consensus on the best approach. Over time, with careful scientific work, this process will help those of us who aren't specialists in this area, including the general public, gain a clearer understanding of which images of these two famous black holes are more accurate. And that's it. Thanks for joining us on this journey through the fascinating world of black holes here at Spaceverse. We dove into the latest debates surrounding the Event Horizon Telescope's images, exploring the intricacies of radio astronomy and interferometry. Stay tuned as we continue to unravel the mysteries of the cosmos.